everyone, welcome to my YouTube channel. I am Madam Rosmaya. In this video, we are going to discuss on PU Physics Semester 3 topics, use of thin lens formula in combination of lenses. So the formula is 1 per U plus 1 per V equals to 1 per F. Okay, many optical instruments such as telescope and microscopes use a combination of 2 or more lenses. So recall to what we have learned before, the thin lens formula is given by 1 per U plus 1 per V equals to 1 per F. So U is the object distance, V is the image distance, F is the focal length. So we have discussed on how to derive this equation in the previous lesson. From this equation, the thin lens formula is a mathematical way to do ray diagrams with algebra instead of drawing lines on graph paper. So in lens combinations, the image formed by the first lens becomes the object for the second lens. So this is where object distances may be negative. From what you've learned before in Form 4, Form 5, okay, usually the U is always positive in your solving problems. But for the Sem 3 Physics, so we are going to discuss on the topics where we get U is the negative. So we try this question for the combination of lens, convex lens and concave lens. So we are going to determine the final image if the object is here at the distance 30 cm from the convex lens. And the focal length for this convex lens is 10 cm, and for the concave lens, the focus length is given by negative 10.0 cm. Negative because this is the concave lens. Okay, so we do separately for convex lens and concave lens. So we do for convex lens first. So we can ignore the concave lens. So from the formula, 1 per U plus 1 per V equals to 1 per F. So 1 per U, so U is 30 cm. Then V1 is, we are going to determine for V1 means the image distance for the convex lens, for this convex lens. So for this convex lens, F1 is 10 cm. So we get V1 equals to 15 cm. So 15 cm is measured from the convex lens. So it's about 15 cm here. Okay, by drawing in the graph given here. So 30, 40, and in the middle between 40 and 50. So 15 cm from the convex lens. Okay, next we are going to calculate for the concave lens. So this is the principal axis drawn along the horizontal line here. So when we draw the ray diagram, from the object we draw a straight line, and then it is refracted towards the normal, okay, because it passed through the different medium here in the convex lens and towards the first image here. So we do the same for another ray. Don't forget the arrow. Okay, this is where the first image is formed by the convex lens, 15 cm from the convex lens. And this part must be drawn dotted line because this is imaginary ray. Okay, so the solid lines represent the actual ray. Why? Because this is line ray that pass through the concave lens. So we don't know what happened yet here. Okay, so this is drawn as a dotted line. Okay, so we continue for the second part, for the concave lens. Okay, so for concave lens, we can take this image as a object. Okay, for the second calculation, we ignore the convex lens, so we just refer to this concave lens. So using the equation 1 per u plus 1 per v equals to 1 per f, so the u is measured from the concave lens. So we ignore this convex lens, just refer to the concave lens. So the distance, object distance measured is 5 cm from here to here, 5 cm. Just now 15, so minus the 30 to 40 here, 10 cm, so here only 5 cm. So we can substitute 5 cm into here, and it is negative because this object is the virtual object, because it should not be there. Okay, it should not be here because of the imaginary ray just now. It's supposed to refract. The ray here supposed to be refracted away from normal. Okay, so it must not be here for the for this object image. For this object, this now is the image from the convex lens. Now becomes object, so it is a virtual. That's why we put negative 5 here. The sign is negative. Okay, V2 we are going to determine, and the F for the concave lens is negative 10. So we calculate, we get V2 equals to 10 cm. So this V2 is measured from the concave lens. So this is the concave lens. So it is positive. So that's mean it lies at the same area of the O2. Okay, object 2. So somewhere here. So after pass through the concave lens, so the ray is refracted away. Okay, by 10 cm here, by 10 cm distance from the concave lens. So somewhere here. So you can continue drawing the ray. This is the actual ray. It's supposed to refracted away from the normal after pass through the concave lens. And don't forget to draw the arrow. So the solid line represent the ray that should travel along this path. Okay, and the dotted here is the imaginary ray for the first image to form after pass through the convex. I2 is image form after pass through both convex lens and concave lens. Okay, so this is the answer. The final image from 10 cm distance from the concave lens. Okay, we've done for the first example. So we try one more example. Okay, this times we try to get where the object where the object is formed here. Okay, if the final image is at infinity, so we do the calculation backward. We are going to determine where the object is supposed to be for the final image here to be at the infinity. Okay, let's start now. Okay, we use the lens formula. Okay, and we use the principle of reversibility of light. So what is meant by the principle of reversibility of light? So the principle stating that if the direction of the light beam is reversed, despite the number of times the beam is reflected or refracted, it will follow the same path. So we can draw the ray diagram backward. So we assume that the image at the infinity, this image become object. So we start with the concave lens. We ignore first the convex lens, so we do for the concave lens. So this is the principle exists. and the image at infinity now becomes object. Okay, we assume this as the object. We use the principle of reversibility of light. So that means the U is at infinity. Okay? So parallel ray here shows that the object is at infinity. Okay, for concave lens, F is negative 10 cm. So we sub into the thin lens equation. 1 per U plus 1 per V equals to 1 per F. So U is infinity, V1, and then focal length negative 10. So we get V1 equals to negative 10 cm. So this is the image form for this concave lens. So 10 cm is negative, so that means it's on the same area here, same area of the O. Okay, and this is concave, so the image here should be virtual. So correct lah, we get negative here, should get negative because it's virtual. Okay, so you draw the image here at about 10 cm here, 10 cm from the concave lens. So measure here 10 cm. Then you draw the line, so as it is as if the line here or the ray here comes from the I1. Okay, so this line must be a straight line. So here also must be a straight line. Okay, so for the actual line should be here, the actual ray, and then refracted away from the normal. Okay, because it come out from the denser medium to a less dense medium, so refracted away. Same goes here. This is the ray, actual ray, and then refracted away. Then after this projected lines drawn here is dotted line, because this is the imaginary ray, which is we can imagine that it comes from the image one here. So that's why here must straight line. Okay, now after the ray pass through the lens, it should not go straight here, so it must refracted away from normal. So we draw dotted line here. That's why this is dotted line. This is the imaginary ray. Okay, it should not go straight after pass through the convex lens. So for the second part, we are going to calculate for the image formed by the second image formed by the convex lens. Okay, so now for convex, we use the principle of reversibility of light also for convex lens. So the I1 just now becomes object for the second calculation. So now here becomes object, and the distance from the convex is 20 cm. Here is 10, so another 10, so become 20 cm. So U2 is 20 cm, F is positive cm, because this is a convex lens. F is positive. Okay, and the object distance is positive because this is not virtual. This is real image. So for the convex lens, the object distance we calculate just now is 20 cm. So this 20 cm is larger than the focal length. If the 20 cm, the object distance larger than focal length, so the object, the image or the object form is always virtual. Is always real. The image form is real. The object also real. Okay, so that's why here is positive. Okay, now we substitute into the equation here. So the U is positive, V2, then here substitute F, focal length 10 cm into the equation. So V2 is 20 cm. We get positive because the image is real. So where does it form? So it form here. It lies on the opposite side of the object here. Okay, so now to draw the ray diagram, we complete here. This is 20 cm, 10, 20, 30, so 20 cm. So this is the ray should be after pass through the the convex lens, after pass through the convex lens, the ray is refracted towards away from the normal, so towards this point. Then forget the arrow. Okay, so this is using the reversibility of light. Okay, now go back to the question. We want the where the object is if the final image is an infinity. So again, we use the principle of reversibility of light. So we just change the direction of the arrow here. Okay, change the direction. It will follow the same path. Okay, the ray diagram will follow the same path. So from the principle of reversibility of light. So this is the actual direction of the ray. Okay, so now the image just now we rewrite as a object. Okay, this is where the object is supposed to be. So what is the answer for the example 2? Where is the object if the final image is infinity? So the object is at 20 cm, 20 cm in front of the convex lens. Okay, that's the answer. Okay, that's all for the 2 examples to be solved in combination of lenses. Okay, thank you for watching.